So in the previous video we just transformed the existing variables, but in this video we're going to add more variables. So let's do a low dimensional example to kind of show how that can increase the ability to make more complex decision boundaries. So just wait, I forgot to change your view here. Come with me. So here's some positive examples and some negative examples. This is a one-dimensional example, so the input space is just the real line, and just imagine that it just happens that all of the negative ones are in the middle. So if you were to do classification in the usual way here, you would get an expression like W0 plus W1 times X1, and then an inequality like this would be the thing that gives the decision boundary. So for example, what kinds of things could you express with this? Well, you can make any kind of cut here using a line, and then you would be able to shade in a certain direction, like let's say this direction. So you would be able to correctly classify all of these as positive and correctly classify all of these as negative, but then you would not be able to classify these positive ones correctly. And so this would be like an example of a one-dimensional, non-linearly separable data set. So, let's just say that this is the x1 axis, and now let's add a new variable, which is not really new. It's going to be just x1 squared. I guess you could call it x2. Yeah, let's do that. So x2 is just equal to, maybe I should just say that's x2. Okay. And now I'm going to plot, what is this? I forgot about, I was going to have to actually do some algebra here. For the sake of argument, let's just say that that's the origin right there. So I'll put a line right there. Okay. So this happens to go exactly through the origin, and it's a good thing my handwriting is so perfect. So let me just write the relationship here. X2 equals x1 squared. All right. So what we've done is we've embedded this data in a higher dimension. So it's still one-dimensional, but now it extends. It exists in two-dimensional space now. So these negative examples that were down here on this axis, now we can imagine them being on this line. So now there are sort of four, or a few anyway, points that we're no longer thinking of them as being on the x1 axis, we're thinking of them as being on this curve, which is a parabola. And we'll take the positive instances and we'll copy them up here too. So they're just going from the one-dimensional axis up to the corresponding point on this one-dimensional curve. So this is like this is an embedding of a one-dimensional instance space into a higher dimensional space. And the point of doing that is now we can do with a linear relationship in the higher dimensional space some things that we couldn't do with a linear relationship in the lower dimensional space. So now if I want to separate these negative examples from these positive examples in the two-dimensional space, it's very easy. I can make this linear separation between the two. Whoops, missed one. So like this. Okay. All right. So now if I shade this upwards like this, now I have classified all of these data points 100% correctly. So I embedded the lower dimensional space up into the higher dimensional space. The image was really still just one dimension, but because it embedded in this kind of curvy way, I was able to make a linear separation in the higher dimensional space that I wasn't able to make before. Okay, great. So you can totally generalize that whole situation. So let's do an example. So here I've just created some data, some two-dimensional data, And it's just normally, it's distributed with the normal distribution and two variables. And here I've already classified it. In the toy example, I just classified it according to which side of this line it was on. I just made it up because that sort of split the data in half. But then after I got the linear separation, I kind of perturbed it a little bit, and I flipped 5% of the values. So that makes it a little bit non-linearly separable. Okay, so here it is. Here it is separated with the line that I used to do the initial classification. And when I did the flips, it just happened that these are the ones that became altered. And the error here achieved by this is 7 or 8%. That's the in-sample error. What is the out-of-sample error according to this method? Let's take a poll. Well, the out-of-sample error will be 5% because just because of the way I engineered the data here. So if I had more data points, the in-sample error would be closer to 5% because this original line would classify everything correctly except for the 5% that get flipped, which it would classify incorrectly. So let's make our hypothesis space more complex. So now I'm not altering x1 and x2. I'm adding a bunch of new coordinates here. So this is like adding columns to the big data matrix. And so I add x1 squared, x2 squared, x1 times x2. So this lets me do all quadratics here. So these, just up to here, now we can do all circles, ellipses, hyperbolas, and other conic sections. And then I decided to add even more. So here are the cubes and some quartic terms down here. So what we've done now, instead of embedding R1 into R2, which is what we did before, now we've embedded R2 into R10. Of course we can't visualize R10, but it's useful to think of it as being there. So just like before, we don't, when we did the parabola didn't land on every point in two-dimensional space, right? Oh, sorry, I didn't bring you along with me. I'm going to make that mistake from time to time. When we looked at the parabola, this is just a very skinny piece of two-dimensional space. And when we transform our data set, when we do the embedding, most of the two-dimensional spaces, it remains empty. The same thing happens in this higher dimensional analog. So most of 10-dimensional space will stay empty. We're just embedding this two-dimensional space into it in this way. And just the way the parabola was curvy, you can kind of think of this as being a wrinkly subset of 10-dimensional space. And so we're going to be able to use a hyperplane in 10-dimensional space to make some cuts here that you couldn't achieve in a linear way when it was still embedded in the lower dimensional space. So you can imagine just sort of like wrinkling this up a little bit. Okay. So we go from the X matrix to the Z matrix. So this is just boring numpy stuff. You know, here's how you add all those columns if you want to. And I use our logistic regression with that we did a couple periods ago to do this. So here's gradient descent, and this is the fast expression for the logistic regression gradient, and here are the parameters that I'm using for gradient descent. So we get this W, which is a 10-dimensional W. So this is 10-dimensional problem now. So I get these, just like in the case of the parabola, in the higher dimensional space you have a sort of a higher dimensional hyperplane. So this will be a hyperplane in 10-dimensional space. And this is just stuff we need to do the logistic regression. This is I'm doing a contour plot, so I'm using mesh grid. Here are the variables. We go through, what this is doing is it's just it's just taking the dot product of W and what we would call Z bar. And then we apply the sigmoid function, and I thought it would be cool to kind of look at the soft decision boundary. This is after applying the sigmoid function. Remember, logistic regression gives you probabilities. So now it's assigning a probability to every point in the input space. And so over here it's very certain that these are positive instances, and over here it's very certain that these are negative instances. And then along here it sort of isn't so sure. So where it's kind of this color, there's a 50-50 chance, and so it really has no idea right along the boundary. So notice that this, of course, is not a linear boundary anymore. Now it's curvy. And it achieves higher accuracy. And now we'll harden it up here. So I force it to make a decision. So we thresholded it so that now it just says yes if the logistic regression predicts a probability above half. It just says yes, and otherwise it says no. That gives you a hard decision boundary. And the error here has gone down quite a bit. It's gone down to 2 or 3%. And we know that that is sort of lower even than the inherent error of 5%. Okay, but is it really better? What is the out of sample error of this hypothesis? Is it going to be better or worse than the out of sample error of the linear boundary that we started with initially? We know that the out of sample error of this boundary is 5% because we know exactly how this data is generated. Okay, so let's add more points and see what happens. So here we had just a few, like 30 or so. Now we have 400. So this gives us a better estimate of what the out of sample error of this decision boundary will be, and it goes up to 8%. And so that is probably a pretty good estimate for what it really is. You know, it'll be 8, 9, 10%, and it'll actually be higher out of sample error than the out of sample error of the simpler boundary. So that happens when you overfit the training data, and when you make the hypothesis class more complex, it makes it easier to overfit the training data. If you can imagine what would happen if we just kept making this thing more and more complex by adding more and more variables. Eventually it would just cut out exactly, if you gave it enough flexibility, it would just put all the blue ones exactly on one side of the curve and all the red ones exactly on the other side of the curve, and it would have perfect classification accuracy on the training set, so the end sample error would be very low. But because it's so convoluted and complicated, it's not really capturing the essence of how the data really works. You know, the data really works by being split across this line plus a little bit of noise. So that's what causes overfitting. You sort of memorize the training data, and even as your end sample error goes down, you sort of get a less and less generalizable decision boundary. So this is a problem in machine learning. It's sort of it's a trade-off. You have to have a hypothesis that has exactly the right level of complexity for the data that you have, and we'll talk more later about how you do that. But just right now, since this is a short video, to end it on a simple rule of thumb, you can kind of afford to have about 10 times as many columns. Sorry, you need the number of rows to be at least 10 times the number of columns. So here, how many columns did I have? I had 10. But how many rows did I have? I had, in this initial case, what was n? I'm sorry, I'm making you dizzy here. Where do those points come from? I think it was 30, right? Here, oh sorry, it's 40. So I had 40 data points, but I had 10 columns, and that will lead to overfitting because they're, it's like some hypothesis is just going to get extremely lucky. We talked about this a long time ago. Like if you have 1,000 people flipping coins and you ask them all to flip a coin 10 times, there's a good chance that one of those 1,000 people will happen to get heads every single time, but that's just luck. It's not skill. So here we're getting a hypothesis that has a low end sample error, partly because it's good, but partly also just because it's sort of a freak that happened to be kind of lucky in a certain way. It got lucky with respect to the particular training data that we had. We could have had other data drawn from the same data distribution for which it was less lucky. And so that's why it's overfitting. It's too lucky. And the more columns you have, the more likely it is that you're going to get some lucky freak. But then the more data you have, the less likely, the harder it is to be lucky, because you have to get lucky on all of these points, not just a few of them. So just as an empirical observation, when you have at least 10 times as many rows as you have columns, overfitting is not a super huge issue, but that also depends on other things. We're just talking about linear models right now. Anyway, I am talking too much. It's time to stop this video.